Hi students, Ms. Deer back on the mic here. We have been talking about iterated integrals, and we know that the double integral of a region, dA, will just give us area. And we also know that if we stick a z equals an f of xy into here, we take the double integral over the region of f of xy dA, this will give us volume. And we encountered some integrals that were really just going to be hard to solve in rectangular coordinates. So just a reminder on polar coordinates, we have x is r cosine theta, y is r sine of theta, x squared plus y squared equals r squared, and tan theta equals y over x. And all of this gives us points that are r theta instead of x, y. So we want to turn a double integral in terms of fxy dA into a double integral of r and theta. Now this region r is going to be translated into a region in terms of r and theta. So right away, this is going to turn into f of x, which is r cosine theta, y, r sine theta, and then what are we going to put on the end here? So if I have a function in terms of r equals, here's r1 and here's r2, and I'm going to sweep this out this way and try to find some area between here. So my change in r, so I'm going to go out to some arbitrary point here, and I'm going to make some little sectors. So my change in r is going to be r2 minus r1. And my change in theta is going to be some theta 2 minus theta 1. And I know that the area of a sector is 1/2 r squared theta. So this is going to be from r1 to r2, my area is going to be 1/2 of delta theta times r2 squared minus 1/2 delta theta times r1 squared. And so if I can take this piece out of both, I get 1/2 of my delta theta times r2 squared minus r1 squared, which we know we can factor into a difference of two squares. So we get r2 minus r1, r2 plus r1. Now this is my delta r, and this is actually just how far I have gone out. So the area of this sector is r, because I have two of these, so two of these, so 1/2 delta theta 2r, 1/2 of 2r times delta r times delta theta. So this turns into r dr d theta. So the really important takeaway here is that if we're going to come up with an integral in terms of polar coordinates, I have the double integral over some new region of f of r cosine theta, r sine of theta, times r dr d theta. We need to put this r in every single time. So let's give you an example. If I have the double integral from 0 to pi fourths and 0 to 4 of r sine theta cosine theta times r dr d theta. So this is all saying, this piece right here is telling me my r values are going out from 0 to 4. My theta values are going from 0 to pi fourths. So I'm looking at this little wedge here is my region. I'm integrating this over this region. But to evaluate it, we just start on the inside. So we have two r's. So the antiderivative of r squared is r cubed over 3 from 0 to 4, which is 64 over 3. That goes back inside my outer integral. So I have the integral from 0 to pi fourths of 64 over 3 sine theta cosine theta d theta. Now we're in our happy place. You can hear my dog barking. He's so excited. I see something and its derivative. So this becomes 64 thirds sine squared theta over 2, evaluated from 0 to pi fourths, which is 64 thirds times 1 over rad 2 squared, which is 1 over 2 over 2, which is 16 over 3. So let's try one where we get to convert it from rectangular to polar. So let's say I have the double integral from 0 to 2 and 0 to 4 minus x squared, x dy dx. So this is a half circle, but I'm restricting it to only the first quadrant. So now it's a quarter circle. All right, so it's part of a parabola. Sorry, let's make it rad 4 minus x squared, so it's part of a circle. So then I'm going to get, this is going to turn into the double integral. Now my x is going to be replaced with r cosine theta. dy dx is going to turn into r dr d theta. Now, my r values are going from 0 out to this quarter circle, so from 0 to 2. And I'm only in the first quadrant here, so I'm going from 0 to pi over 2 for my theta values. So when I take the antiderivative of r squared, I get r cubed over 3 from 0 to 2, which is 8 thirds, which then gets plopped inside that outer integral. So I have the integral from 0 to pi halves of 8 thirds times cosine theta d theta. Again, this is our happy place. This gives me, let's see, 8 thirds sine theta from 0 to pi over 2, which is 1 minus 0, so 8 over 3.